the very end of last time. So as you can see, I did the inverse graphically, interchanging x-axis and y-axis. The diagonal did not work out well, so let me try erase the diagonal. It was not 45 degrees, so that's why when I flipped it, it was not matching itself when overlapped. So let me try to do the 45 degrees again appropriately. No. Line, 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 line. Okay. Okay, so it happens to be touching the graph of the function over there. Okay, so I'm doing 45 degrees again on the other one. Okay. Okay. Okay, so now let me try to overlap so that the relation is clear. Okay, so like this. Okay, so so if you can see it, so the new one coming from the right, and then the x's are the same. The diagonal is the same because when you flip the diagonal around the diagonal, you have the same diagonal, right? So there you go. So the shape of the graph could be anything. Anything can be flipped because it is simply a transformation of the plane. So anything you can draw on the plane can be flipped this way. But we certainly concentrate on, for the most part, on graphs of functions. So as you can see, I carefully drew a function that is, even though it has this twist, it is still one-to-one. If you look carefully over there, where it looks almost horizontal, but it's not. Okay, so it is still going up, and that is why it is still one-to-one, and that's why it's invertible. The other example that I was unable to find, this is from last week, so it's a bit better because the graphs or the x's are marked, so you can see how they have been flipped. And once again, I can add the diagonal, okay, like this, and once again, I could try to overlap. Okay. Okay. So it is unpredictable, and either you think in terms of one operation, one flip, or you split it into two operations, one flip around the one of the axes plus the rotation 90 degrees. Okay, either way, but you cannot really, it's not a shift. There is no shift involved, and there is no stretch involved in all directions. Okay, so it is what it is. It is a flip, and there's really no other way to do it. If you cannot do it like that, you don't have with you your paint like this. Okay, so what do you do? The answer is you do it point by point. So that certainly needs to be illustrated. Let me go back. Point by point. So just like you can take the graph and shift it point by point, you can also flip it this way, point by point. Okay. Okay. So I'm gonna overlap then, and then just demonstrated that it is really not that hard if you know what's happening. You cross the diagonal. That's what's happening. You cross the diagonal at 90 degrees, just like you cross the axes. Remember those flips? Just to refresh your memory, these were if this was the axis. And then the point would cross like this. That's a flip. This is a flip of along this horizontal axis, which makes the flip itself vertical. And what's so special, if you look carefully, these are the same distance, and you go 90 degrees. That's what the flip is. Across the axis at 90 degrees with the same distance on the other side. That's what the mirror image is. And like I said, the point of this is that you do it one point at a time. You don't have to do the whole thing at once, which may be confusing. So if you want to flip something, you can do it by point, especially if it's a curve. Pick 10 points, or even last 5 points might be sufficient, and flip them. Okay? So in retrospect, that's what I should have probably done, but you can probably see it here as well. So if I pick, say, I take the lower one, okay, so, and I pick these points, and these, you don't have a lot, don't need a lot, so I pick these 4 points on the original, which one was the original? The original one, yeah, on the left, okay, so I pick these 4 points and find their counterparts one at a time in the manner I just indicated, okay, so you go perpendicular across the, diagonal, and then find the distance. I even chose the points on the graph on the diagonal. What's so special about them? They don't go anywhere. Okay, just like with if you pick a point on over there, you're doing a vertical flip. The points on the axis don't go anywhere. Okay, so same thing. So 4 points just happens to be sufficient here. So I pick. So this point is the same. This point will go across, same distance, 90 degrees, okay? This one is not going anywhere, and that one is going across in the opposite direction, once again, 90 degrees, same distance, okay? Let me do it again, so to make that point, because they already see the answer here, so let me go to, yeah, okay, so you can see them existing separately, and then you can do it point by point. Let me do it again, so that it would be more convincing, I suppose. So if I go to this one, so let me take the one on the left, and produce the one on the right in that manner. Okay, so. Okay, so once again, I pick a few points on the graph. So endpoints, what are points are good for it? Points that are the endpoints of the graph, the points where it crosses one of the axes or the diagonal. Okay, so all of these are the best points. Okay, so I'm picking then these. I pick this one. I pick the 2 points in the diagonal. I pick one on the y-axis, one on the x-axis, and one on the end. Okay, so these are 6 points that should be enough. Okay, so let's start with the simpler ones, and the simpler ones are the ones on the simplest ones are on the diagonal. Okay, so I pick those 2 green points on the right, and so these points don't go anywhere under this flip. So I immediately have 2 new ones. Okay, so the blue ones are the new ones. The green ones are the original. The blue ones will be on the graph of the new function. Okay, so I already have 2. Okay, what if I pick this one? Where is its counterpart?
Would be on the new x-axis.
Right. So if it was on the old y. Right, so on the horizontal axis. So if it was on the vertical axis, it will be on the horizontal axis. So that way you can just draw carefully the perpendicular line like this, and you know where you're going to supposed to stop. You will stop once you reach the horizontal axis. So that is my point, new point. Okay, so you don't even have to measure anything, even though in general you do. But when you know the direction, 90 degrees, and you know the destination, the horizontal axis, then you got it. Similarly, if I pick that point on the red on the left, on the red horizontal axis, its counterpart will be where? The point on the left, on the red axis. Yeah, on the vertical axis. So once again, I don't have to measure anything. All I have to do is just carefully, and you can do it by hand. I'm doing it by hand, not anything else. So I go perpendicular to the diagonal, and then continue on until I cross the x-axis. Well, the vertical axis, the y-axis. Okay, so that creates a point one more point on the graph. Okay, so I'm left with 2 points, and they're fairly close to the diagonal, so it's fairly straightforward to draw a line like this, 90 degrees. Just estimate with your naked eye how far you're supposed to go in that direction. The perpendicular direction, the angle is important, so you have to make sure that this is 90 degrees. The distance is you probably can estimate pretty easily with your naked eye, or use it the way I do it. I just measure it with my fingers, and then I have the same distance on the other side. Okay, so if this is my distance, and on the other side it's here somewhere. Okay, and I create a counterpart of that point. Okay, so once again, this one is crossing left to right. This one crossing this way. So they are all on this, happens to be on the same side. And then point here. Okay, so you have 6 points, and it's usually enough to get the general idea of what the graph is. If either you connect them just in some kind of semi-random, not random, but semi, just one stroke if you can, or you can once again still match the pieces that are missing with the pieces that you have, because they have to be, they are transfer, they are mirror image of each other. So if I start from the left, I know where I'm supposed to go, and the counterpart edge or piece of the graph is over there. It's almost a straight line, right? It's almost a straight line, so I'm roughly, that's what I'm doing here, roughly like this. Okay? As you can see, there's a match. There are 2 pieces, and they are mirror images of each other. Okay? The second part is slightly tricky. It has a curving from one to the other, but not too complicated, so just do it like this. It doesn't have to be exact. So it goes straight, then turns, and then a little bit straight more. Okay? Here, it has goes straight first, the next one. It goes straight first here, and then kind of slows down and start to make the right turn, like this. Okay? Okay, this one is almost along the diagonal, like this. And finally, this one is almost a straight line. Okay? So if you have a grid, in fact, I could have used the grid here as well. Makes your life easier, whether you do it on a piece of paper, or so if you have a grid on a piece of paper, that will help. Or if you're doing it by hand using such as paint. So any questions about this? Okay. Okay, so as I said, we are wrapping up this topic, but inverses, so that's not really the most important part. We just discussed it. Is imagining what the graph of the inverse looks like. It's kind of interesting because we have produced a new function. We want to know roughly what the graph looks like. But the idea that we started with about the inverse is that the functions that undo the effect of the original function. Okay, so that is much more important. And it is so, in fact, important that it comes up in, it gives you a new view of things that you may have seen, well, definitely have seen before, and that is solving equations. Okay, so, which have really come up just yet. It is a challenging topic in the sense that there's misunderstanding of what it means to solve an equation to begin with. And then we talked about that a little bit already. And then secondly, what it means, how do we solve it? Okay, so let me review quickly of what we have talked about first. So given an equation, it doesn't matter what the equation is. Say, it doesn't matter whatsoever what the equation is. So what does it mean to solve it? So just, well, you remember what it means? What does it mean to solve an equation? So not how, but what is that you have in the end that you know that that you are good. No, that's not a solving an equation. Solving an equation means find all x's that satisfy the equation, the end. There's nothing else. Once again, it's not about how, it is what it means. Okay, so you have to find all numbers x that when substituted, that's what I mean by satisfy the equation. When substituted into the equation, you have equality between left hand side and the right hand side. You can easily check it. If I plug in x equals 0, then yes, right. I plug in 0, 0 minus 0, 0 sine of 0 is also equal to 0, so then there you go, you have 0 equal to 0, and then that's how you know that the equation is satisfied. You plug in, there are no other variables but x, you replace x with a number, which means that you have nothing but numbers. On the left a number, on the right a number. If these two numbers are equal to each other, then the equation is satisfied, and what you have found is indeed a solution. So that's one challenge. The second challenge is to finding all of those x's. So even though I have found one, it's not it. I still have to find the rest of them. There might be more. I'm not sure. That doesn't matter. So that is the question. So that you have to understand this before you start thinking about how. So that's the other question of how to deal with that is how, and that is a big topic that it really has no ending, but this one does, and it is a fairly short question and a very short answer. So every time you embark on a solving equation, you want to know what is that, where you want to be at the end. Okay, so you're supposed to find all x's that satisfy the equation. Okay. If you have more than one equation, then same story. So all the equations have to be satisfied for whatever x's and y's that you plug into it. So equation is dependent on this unknown number, but it is a number, and then when that unknown number becomes a known number, then you'll know whether or not this is true or not. So 1 squared minus 1 is equal to sine 1. No. Okay. So in general, if you have no slightest idea of how to solve it, any kind of method of solving equation, trial and error, which is what I did, and at least there's a chance that you run into something. Ultimately, that's what it is. So I plug in 0 and I have yes, and I plug in 1 and I have no. Okay, and that's what the story is about. The rest of them are just shortcuts, so you don't have to test infinitely many numbers, and you plugging them in and testing. So then you have a better ways of solving those equations. At its simplest, it is either straightforward algebra. 3x minus 1 is equal to 7. So you just do algebraic transformations, which deserves separate discussion. Like this. Okay, so this is a separate discussion, but so this is how you solve some of the equations through algebraic manipulations. Okay, so and then well, the second example would be a quadratic. Say 2x squared minus 7x plus 1 equal to 0. So there's somebody who already did work for you, and then you have a quadratic formula, and you just you don't have to do any manipulation, nor testing, nor trial and error. So x is equal to 7 plus or minus 7 squared minus 4 times 2 over 2 times 2, and then just finish the computation. You'll have your answer. Okay, so that is rare. When you already have either the linear equation in the first one, you can just manipulate a little bit and you have the answer, or you have a quadratic formula, so you plug things in, and you have your answer or answers. Or remember, there are 3 possibilities. You either have 2 answers, you have 1, or none. Okay, but that is the answer to the question. Okay, so. So what does it have to do with the universes? And that is, it gives you at least one method of solving equations that is very common. So third example is, say, we've seen this, say x plus 1 square root is equal to 3. And so what do you do? So it is an equation. What does it mean to solve the equation? Once again, the same story. You need to find x, or x's, which when plugged into the formula will give you the same number on the left as on the right. Okay. So that's what you have to have at the end. But the question now, slightly moving forward, is how, and the answer is the plan or the strategy is, which I apply in number 1, but maybe not in number 2, is because it was solved for us. You need to isolate x. Isolate means that there is x on one side and there is nothing else on the other, and there is no x on the other side. So x on one side, no x. Well, x only on one side and no x on the other. That would do the trick. Okay, because just like I just did it. So like this or like that. It is still an equation, by the way. Still an equation. That's also should be remembered that the answer frequently is whenever you haven't written the answer in the form of a solution set. Remember, you might face, as you just did, an equation. It just happens to be an equation that is a final equation because x has been isolated. So on the left you have x, and you have on the right you don't have any x. Okay, so that's the isolation. So sometimes it's hard. The quadratic equation is actually pretty hard. If you think about it, you have x's appears twice, so you cannot do the manipulation that you have in the first line in order to isolate x in that manner. But the third one is actually simpler than number 2 because you can actually isolate x. The question is how. So how do we isolate x in this example? Yeah, so the answer is square both sides. This is a crucial operation and crucial idea. What is this? What is the meaning of a square? Square is a function. So this is a function. The square is a function. So say, let me call it, say, g of y equal y squared. Okay, so square both sides. What does it mean? It means let's think in terms of functions again. So we have two values that we want to be equal to each other, so we assume that they are, and then we apply a function to both sides. Okay, so I have a square root of x plus 1 here, and I have 3 there. So I apply, and they are equal to each other. Okay, so then I apply a function, a new function. I have x squared plus 1 squared, and I have 3 squared. Okay, so that's what it means to apply a function to both sides. So literally, I plug in that value that is on the left into my function. So y is equal to x plus 3, and y equals to 3 is also plugged into this function. Okay, so now the key is why does it work? Why does it work? Because based on what we know about functions, the outcome is they're still equal to each other. Okay, so they're equal to each other. Why? Because that's the nature of function. Remember, you cannot have this. Okay, so if you have an element of your domain, and you apply a function, you cannot have two outputs. So only one output. So that's why it's supposed to work, producing a new function. So this cannot happen. You cannot break two. You cannot have two outcomes for this two outputs from the same input. So if the two inputs are equal, then so are the outputs. Okay, so that is why we get a new equation. new equation. So, and then I have, as I said, x plus 1 squared is equal to 3 squared. Okay, so so new equation. Then the hope is that it is better, but the plan that has been just described works no matter what the function is. So you have to be wise and have foresight to choose the right function to apply in order to achieve the ultimate goal of isolating x. But really, this idea will work. This idea will work with any function that you can think of. So you can. So we decided to square both sides. What if we had cubed both sides? I mean, it would be pointless, but the result will be the same. It is not. It will be moving in the wrong direction as far as the goal is concerned, but it would not be a mistake because the result will be still correct. You would have produced a new equation. So let me illustrate. Square root of x plus 1 cubed is equal to 3 cubed. Okay, so it still works. Or I could have sine square root of x plus 1 is equal to sine 3. All of these are good. All of these are choices that you can make. And that the problem is that they're all equally applicable. And you have to know what you're trying to accomplish in order to choose the right one. But they are still produce new equations. Every time you produce new equations, and you may have hit a dead end, but like I said, technically it's not a mistake because these are correct. So your choice of the function was unwise, but it's not a mistake that you have produced. That equation that you ended up with is still correct. It is an equation. If x satisfies the original equation, it would have to satisfy these equations as well. Okay, so that deserves special attention. And when you are trying to solve an equation, you might take wrong turns like this. So I decided to cube it for whatever reason. So it is for you to then to recognize that you are not getting anywhere and go back. But it is very important, however, to make sure that you do it correctly, and then you still end up with the correct equation. Okay, so that deserves a separate discussion of well, maybe not. I think we got it here. So applying a function to an equation. That's what I'm trying to say. Applying a function to an equation produces a new equation, period. Which your goal is to that new equation. So equation, and then you can produce many new equations, like this. So that's the challenge. The challenge is which way to go, even though they are legitimate in the sense that you're not saying something that is not correct. You're not, if you carry out the algebra correctly, but some of them, or maybe all of them but one, are just wrong directions. You got it. There is one that will work out, and the rest will probably not. Even though you might try to circle back like this, and that happens like this. You might try to eventually, if you keep doing it, eventually arrive to the answer. But let's say you want to take the right turn, the right direction from the beginning. So and choose one correct function to apply in order to produce a new equation, which will simpler than the original. Okay, so how do we choose, and how did we choose the correct or maybe the best function to apply? Okay, and the answer is, well, you can probably explain that this choice that was made. Why was it a better choice than these two? See, these are also choices that produce new equations, but they were unwise. Why did you choose to square it? Because it cancels out the square root, and in light of recent discussion, what is the relation between the square and square root? They are inverses. So that's what we were trying to accomplish. If x is inside of some function and we want to extract it, this is the x. What do? We apply the function that is inverse of the function that stands in the way. Okay, so square root stands in the way. Okay, this one. The square root stands in the way. It is between us and x, between x being isolated in one side, and so we need to get rid of it. Get rid of it, and how do we get rid of it? We apply the inverse because that's its inverse, and because the inverse will cancel its effect. Okay, so where's here we are. This is the new equation that we have produced, and as it was inside was which we just talked about. The inside was to cancel square root by the square, and so the end result will be the equation that is simpler than the original. Okay, so you might be mistaken, but you will know very quickly whether or not it works out. You have this equation. You have two equations over there, and when you cube. Once you realize, I want to simplify it, and realize that square root and cubic power, third power, would not cancel each other and won't simplify, so that was a bad choice. Sine and square root, once again, a bad choice. But what we have chosen here is a good choice because, let me write it out, without just looking at these two functions. So I have a square root of y, and say, z is equal to square root of y, and say y is equal to z squared. Okay, so we are applying, so this one is present in the equation, and this one we apply. So the inverse. So you observe the function that that is on the outside of our x, and to get rid of it, you find the inverse. And you apply it to both sides of the equation, which is what we did 3 times. Okay, the choice was correct, which is now to discover, because if you can verify, certainly you can substitute what is it, y equals z, substitute z, which is square root of y, into z squared, and you'll have the right answer. So this is the simplification that we're after. What is it? Z squared is equal to square root of y squared, and it is equal to y, well, at least for as long as y larger than or equal to 0. So that's another thing to worry about. It came up just recently. Remember, the square root of the square is not a one-to-one function, so its inverse only same for the square root only exists when we limit our domain to codomain to non-negative numbers. So that is still to worry about, but at least in this particular case, we do end up with a simplification. And so what do I have here? I have square root of x, the square root is gone, so let me do it again. So square root of x plus 1 squared is equal to 3 squared, okay? I turn it into 9 on the right, and on the left I have x plus 1. And once again, I have a limitation that x plus 1 has to be larger than or equal to 0. Okay, so if it is the case, then I have x is equal to 10, and the condition is satisfied. The restriction for which the function has to be, the inverse has been applied. The particular inverse was chosen, not just general. So in a way, that's an extra challenge. When your function that you are trying to get rid of is not one-to-one, or it's not onto, or its domain is not everything, then you have to do it one piece at a time, which is exactly what we did. We concentrated on only the domain of y equal x plus 1 larger than or equal to 0, and then we solved the equation because things canceled out. So this square root that was here has disappeared, and we ended up with x plus 1 is equal to 10. Thank you. And the answer is okay. So just to make sure, remember once again what does it mean to solve an equation? You plug it in, and that way even if you have made mistakes, you will know that you were wrong. If you go all the way back to the original equation, plug it in. Okay, so I'll do that. So to make sure that we are correct, so I go to the original equation. Substitute x equal 8 into the equation, which is x plus 1 square root, is equal to 3. Okay, so what do I get? I have 8 plus 1 square root and square root of 9, which is 3. So it checks out. Okay, so what we have accomplished is, okay, so let's reiterate what is that we have accomplished so far. So we're solving an equation. So this is what it means to solve an equation. And are we done? What happened to the clock? Are we done? Yes, that's right. So until we're sure that we have found all of them, we have not solved the equation. So that is the challenging part, making sure that we have found all the x's. We found one, okay, so that's better than nothing. But now we have to make sure that we have found all, which potentially might produce more. It is possible that can produce more. Where is the trouble that might have produced multiple solutions? It was not here. Okay, this transition for x plus 1 equal to 9 to x equal 8 is not a problem. It does not create problems of that nature. It is our square that as the inverse was only limited to these values of y, to these values of x plus 1. So as long as x plus 1 is larger or equal to 1, then we are okay. It works out. So let me write out. We have found all solutions when, for the case of x plus 1 larger than or equal to 0, which is the same as x larger than or equal to negative 1. Okay, so if that was our restriction, then we found all of them. Under that assumption, our function is one-to-one onto, and the cancellation then was legitimate. Remember, the cancellation only legitimate is when the function is one-to-one onto. Otherwise, there is no inverse to begin with. So we were justified to speak of. In fact, probably better to go all the way back and make that point. So square both sides. Where's that business about the inverse? So this is the inverse over here, but it is only inverse for y larger than or equal to 0. So as long as it is the case, you are fine, and the problem is solved. But you split the numbers into potential solutions in half, and then you have to examine the other half. Okay. So then the other possibility is the what if. Well, we're considering the other one. So now consider the rest. It is not really that different, but so assume, well, that shouldn't be too long. So what if x plus 1 is less than 0? Okay. Look at the original equation. So consider the original equation, which is once again square root of x plus 1 is equal to 3. Okay. So what do you see here? Equation and that x's that we are considering. So we could try to solve it. But there is a shortcut. Do you see anything? me circle it for you. So we assume that x plus 1 is less than 0. We're trying to solve an equation that involves the square root of x plus 1. Okay, what does it tell you?
If the original equation is the square root of x plus 1, it can only be negative 1.
What negative 1? Where did you get the negative 1?
From,
If you squared, we are in the same place where we started. Well, the first half, where we just considered the case of squaring it. So, it is a possibility. I just want to. I'm surprised you don't see the obvious. No, what's the what I circled? I would, yes, but I would if I try to square. I'm suggesting not to square. I'm suggesting examine. So maybe consider is not a strong word enough, but let's examine it. Examine the original equation with that extra restriction, x plus 1 less than 0. Okay.
can't find the square root of a negative number.
That's what I was driving at, of course. Of course, there is if x plus 1 is less than 0, then you have a negative number inside of the square root, which is impossible. And that is the answer pretty much. So this is impossible. Okay, so if we concentrate on x plus 1 less than 0, those x's, and we're looking for solutions to our equations among those, then we discover that no matter what number we pick from those and plug it into the equation, we'll get a contradiction. We'll have on the left an expression that doesn't make sense because it's outside of the domain of the square root. Okay, so this is impossible. So what's the conclusion? What's the final conclusion? What? It is. Yes, you can say that. What you should conclude first is impossible. What does it mean? The equation is not satisfied for any x with x plus 1 less than 1. It is not satisfied. In other words, none of those x's is a solution. A solution is the one that when you plug it in, you give you two numbers equal to each other, but it doesn't matter what on the right. That 3 on the right becomes irrelevant because no matter what you plug in, if x is x plus 1 less than 1, you have something that's undefined on the left. It's not even a number. It is nothing. So you have something on the right that is 3, and you have nothing on the left, which means that the equation is not satisfied, which means that whatever x you pick is not a solution. Okay, so what's the answer? The total answer. That's right. 8 is the answer then. So we had a restriction on x's that x plus 1 larger than or equal to 0. We solved under those restrictions, found one of those x's. It is 8. And then we looked at the possibility that maybe there are others, x plus 1 less than 0. We realized that there are no solutions in that region. So that 8 is the only solution. Okay. Okay. So again, the midterm. Okay. So this is the cutoff point for the midterm, and we'll have an opportunity to talk more about it this week. Okay.